Okay, so today we're going to unpack the story of a hidden force, one that connects two of the universe's most fundamental powers. It's a story that actually starts by complete accident, but, believe it or not, ends up powering our entire modern world, from tiny motors to giant particle accelerators. So yeah, let's dive right in.
Just imagine for a second, what if a fundamental force of nature, one that could literally change the entire course of human history, was sitting right there in front of you, just waiting for someone to notice? Well, for centuries, it was.
All right, picture this. The year is 1820. We're in a lecture hall with a Danish physicist named Hans Christian Ørsted. He's in the middle of a demonstration about how electric currents can heat up a wire. And just by pure chance, there's a magnetic compass sitting on the table nearby. What happens next is going to change, well, everything.
So the experiment itself couldn't be simpler. At first, no current, the compass just does its thing, points north. But the very moment Ørsted flips that switch and electricity starts flowing through the wire, bam! The needle just goes wild. It deflects like crazy. Now, there were no magnets anywhere nearby. The only possible explanation was that the current itself was acting like a magnet. And this was the absolute light bulb moment. Ørsted realized that the flowing electric current, which is really just moving charges, was creating its very own magnetic field. This was the first concrete proof that electricity and magnetism weren't two separate things, but were deeply, fundamentally connected. So the connection was finally made. Awesome. But just knowing a force exists isn't really enough. The next huge challenge for scientists was to figure out how to actually describe it, how to measure this invisible force. How strong is it? Which way does it point? How in the world can we calculate it? The first big breakthrough came from a couple of French physicists, Biot and Savart. Their law gave us this incredibly meticulous, piece-by-piece way to calculate the magnetic field. So instead of trying to tackle the whole wire at once, their method is to break it down, calculate the field from every single tiny little segment of the wire, and then just add it all up. So what did they find out? Well, the basic ideas here are actually super intuitive. If you crank up the current flowing through the wire, you get a stronger magnetic field. Makes sense, right? And if you move further away from the wire, the field gets weaker. Specifically, it drops off pretty fast, with the square of the distance, in fact. And here it is, the mathematical recipe they came up with. Now, don't let the symbols scare you. This is really just a precise, fancy way of writing down those two ideas we just talked about. It lets a physicist calculate the exact magnetic field, that little dB, from any tiny piece of a wire dl carrying a current I. And that little symbol there, mu naught, we call it mu naught, that's a fundamental constant of nature. It's the permeability of free space. The best way to think about it is like a universal conversion factor. It basically tells us how easily a magnetic field can set itself up in a vacuum, and it's this fixed number that scales the entire relationship between electricity and magnetism. Now, the Biot-Savart law is amazing because it works for any shape of wire you can imagine, but adding up all those tiny little pieces can get really complicated, mathematically speaking. Thankfully, another brilliant physicist, André-Marie Ampère, came along and found a much, much more elegant way to see the big picture. Ampere's law is just pure genius. It basically says, forget about all the tiny pieces. Instead, just imagine drawing a closed loop, like a magic circle, around the wire. Ampere figured out that the total magnetic field strength all the way around that loop is directly tied to the total amount of current punching through it. It's this incredibly powerful shortcut that connects the cause, the current, directly to the overall effect, the magnetic field. Okay, so let's put these two side by side to really get it. The Biot-Savart law is the universal bottom-up method. It's kind of like trying to figure out a city's population by walking around and counting every single person one by one. Ampere's law, on the other hand, is the elegant top-down shortcut. It's like knowing the population just by looking at the city's overall size and density. For really symmetrical situations, like a perfectly straight wire or a nice, neat coil, Ampere's law is just so much simpler. Now, understanding these laws wasn't just some abstract academic exercise. Oh no! The moment we could predict and calculate the magnetic force from a current, we could control it. We could harness it. This knowledge became the blueprint for building the entire modern electrical world.
And the applications are just everywhere. The spinning of literally every electric motor, the incredible pull of an electromagnet in a junkyard crane, the precise measurements of an electrical meter, and even the mind-boggling power of a cyclotron smashing atoms, all of these are direct, real-world applications of the force made by moving charges.
Here's a really cool example you can wrap your head around.
If you take two wires and run them parallel to each other, the magnetic field from the first wire actually pushes or pulls on the second one. And what's so wild is the direction of that force. If the currents are flowing in the same direction, the wires actually pull together, they attract each other. But if the currents are going in opposite directions, they push apart, they repel. This very interaction is so fundamental, it's actually how we officially define the unit of current, the ampere. How cool is that?
So, let's just step back for a second and look at the whole journey. We've gone from a total accident, a chance observation in a classroom, all the way to a deep, mathematical understanding of an invisible force that quite literally powers every single aspect of our daily lives.
This timeline really puts it all into perspective, doesn't it? In just a handful of years back in the 1820s, the entire foundation was laid, and for the next 200 years, we've just been building on that foundation, creating a world that Ørsted could never have even imagined, all based on that little twitch of his compass needle.
When you get right down to it, Ørsted's discovery did so much more than just link two ideas. It started a revolution. It revealed that electricity and magnetism are not separate at all. They are two sides of the very same coin. Two faces of a single unified force we now call electromagnetism.
And that leaves us with one last kind of mind-bending question. We know that a charge moving in a straight line creates a magnetic field. Okay, but what about a fundamental particle, like an electron, that has its own built-in intrinsic spin? What kind of magnetism does that create? Well, that question, it takes us out of the classical world and right to the doorstep of quantum mechanics. But that, my friends, is a story for another explainer.